what is the function phi prime of x if phi of x equals this integral? Okay, so a couple of things about this problem. There's two things being expressed here that should be a big red flag of like which topic that this is covering. So if you see a function being defined with an integral in it, that's a clue that you're probably doing the fundamental theorem of calculus, right? Where we showed how to take the derivative of an integral with respect to x. The second big red flag here is that there are x's in one, or in this case, both of the bounds. So if you see an expression of x in the bounds and the inside of the integral is actually defined by another variable, it doesn't have to be t, it's just t is the most common, so this variable is different from these variables, that is a clue that you're doing FTC, okay? Now, sometimes in class, I don't know how this was covered in your classes, but a lot of times you would see these problems too, is the d dx would already be out here. So if I see this, I then scan back through the problem and go, oop, yep, there it is. They're going to want me to take the derivative. So that right there is telling you that you are going to do the d dx of this. Now, the conditions that need to be met in order to, it's a very quick, direct process, but the first thing that you need to check about the integral that you've been given is the lower bound needs to be a number. It could be any number, just a number, and the upper bound needs to have the variables in it. If that is true, then it's a very quick path to the answer, and I'm going to explain that in just a minute of what that path is. If you see the bounds are not in the correct order, we reverse the bounds to get them in that correct order. Now, in a situation where they're in both locations, we need to split this up so that we're dealing with each of these separately. So one of the algebraic properties of of integrals, is that you can break apart an integral, and in some cases you can put an integral back together if certain conditions are met. So the property says no matter what your A is or your B is, right, your lower and your upper, you can pick any number in between and split the integral across that number. So let me show you what that looks like. And you don't even have to pick a real number, right? So I'll just call it C because I don't actually know the value of that, and I don't actually know the value of that. So I'm just going to say there's plenty of numbers in between, so let's just pick one and we'll name it C. So the integral from x plus 1 to c of sine of t over t squared plus 1 dt plus the integral, so the upper bound c where you stop needs to be the lower bound of the next integral. So these line up. So you can see that the area that you would in theory calculate here plus the area that you would in theory calculate here would be the same as if you calculated the total area from the original A to B. So this isn't a property that's used just in this situation. You can split integrals up like this with any lower and upper bound that you would like. So then we go to the upper bound. The insides of these integrals are the same. So now I'm in a situation where I've got variables in the bounds, but I only have one in each integral, so that way I can deal with it. Now this brings us back to the conditions that we want to check to see if they're met here. So here, the lower bound is a number. You don't actually ever need to know what the number is. It doesn't matter what the number is, it just needs to be a constant. The upper bound has variables, so this one's okay. This one, we have a number and variables, but they're in the wrong place. So I actually need to switch these bounds. And when you switch the bounds, you multiply the integral by -1. That's another property of integrals. Okay, so now if I want to take the derivative, the way it works is the following. This is a -1, so I still got my -1. So the way you take the derivative of this integral is you plug the expression that's here in for everywhere you see a t into this equation. So this is sine of x plus 1 plus x plus 1 squared plus 1. Then you multiply this by the derivative of this expression, and the derivative of x plus 1 is just 1. So that's it. It's a very direct path to take the derivative in this situation. All right, now let's deal with the second integral. Same thing. Lower bound is a number, upper bound is an expression, so we're ready to do this. So you just plug the upper bound expression in everywhere you have a t. So sine of x squared squared is x to the 4th plus 1, and then you multiply by the derivative of this expression, and the derivative of x squared is 2x. And that's it. That's the exact answer. Now, for some of you that would like a formula, I'll show you there's actually a formula equation for this. So the derivative with respect to x okay, so the derivative with respect to x of the integral from a to u. Now I've picked these letters. A represents the number, u represents an expression of x, right? So think of the same way we use u in u substitution. So there's an equation here with x's in it. And then whatever the function of t dt is. The formula says this is plug u into the function. So you just plug u in for t into the function and then multiply by u prime. So that's what I was doing in each of these integrals.